Aromatic Compounds, Chapter 17. Objectives. 1. Introduction to aromatic compounds. 2. Stability of aromatic compounds. 3. Criteria for aromaticity. And 4. Benzylic reactions. Your goals. By the end of the chapter, you should be able to name and draw aromatic compounds, understand aromatic stability, determine if compounds are aromatic, non-aromatic, or anti-aromatic, predict benzylic reactions. 1. Introduction to aromatic compounds. Aromatic compounds, or arenes, include benzene and benzene derivatives such as toluene and orthoxylene. Benzene derivatives were originally isolated from fragrant oils, hence the term aromatic. However, most aromatic compounds that we know of are odorless. Aromatic rings are a common feature in drugs. General nomenclature. Benzene is generally the parent name for mono-substituted derivatives. For example, chlorobenzene, nitrobenzene, ethylbenzene. The following common names are accepted by IUPAC as parent names and are frequently used: toluene, phenol, anisole, aniline, benzoic acid, benzaldehyde, acetophenone, and styrene. Make sure that you know these. Phenol. If the substituent is larger than the ring, the substituent becomes a parent chain. For example, in this parent chain, there are 7 carbons, so it gets the name heptane, and therefore the benzene ring becomes the branch. The name for the branch is phenol. It is on carbon number 1. Benzene rings are very large. Oftentimes they're represented with an abbreviation, such as PH for phenol, or with the Phi symbol. Here is an example of tetraphenyl cyclopentadieneone. Notice how large it is. In order to make it a little bit easier to draw, the benzene rings are represented by PHs or with the Phi symbol. Di-substituted benzene rings. The terms ortho, meta, and para are used for the location of substituents on di-substituted benzene rings. For example, when we have a benzene ring with OCH3 attached, that is called anisole, and so the branch is on carbon number 2 of the benzene ring, and that's a nitro. We can call this 2-nitroanisole, or because the groups are next to each other 1, 2, it's ortho. For meta, we're going to see the pattern as 1, 3. The benzene ring with the CH3 group is toluene, and we have then a branch on carbon 3 if the carbon that has the CH3 group is carbon 1. This is 3-bromotoluene, or because it's 1, 3, it's meta. For para, the pattern is 1, 4. In this case, the benzene ring with a C double bond OH is benzaldehyde. If we have a group on carbon 4, that's going to be then para. In this case, para-chlorobenzaldehyde or 4-chlorobenzaldehyde. Make sure that you know the pattern. A 1, 2 organization is ortho, a 1, 3 is meta, and a 1, 4 is para. The common names for dimethylbenzene derivatives is xylene. We're going to see orthoxylene, metaxylene, and paraxylene are possible. Again, the pattern is 1, 2, 1, 3, and 1, 4. Nomenclature rules. 1. Identify the parent chain. It is generally the aromatic ring. Often a common name can be the parent chain. In this example, the parent chain is phenol. 2. Identify and name the substituents. 3. Number the parent chain and assign a locant to each substituent. A substituent or branch that is part of the parent name must be assigned the locant number 1. In other words, this carbon must be 1. From carbon number 1, then we can go ahead and number the ring in order to give the carbons with the branches the lowest numbers possible. In this case, 3 and 5. List the numbered substituents before the parent name in alphabetical order. Ignore prefixes except for iso when ordering alphabetically. Go ahead and try to name this compound. Hopefully we got 3,5-dibromophenol. Nomenclature practice. Name the following molecules. Use the techniques we discussed earlier by using the accepted IUPAC common name. For example, the first compound has toluene in it, so use that as a parent name. Hopefully we got 3-bromotoluene or meta-bromotoluene. Go ahead and name the second compound. Hopefully we can recognize that we have benzaldehyde, and chloro is going to be our branch. We have 4-chlorobenzaldehyde as an appropriate name, or para-chlorobenzaldehyde. Go ahead and try the last one. The parent name, anisole, has nitro as a branch. We can call this 2-nitroanisole or ortho-nitroanisole. 2. Stability of aromatic compounds. Note here we have benzene resonance contributors. We may either draw the ring like this or the resonance structure like this. One may actually draw the ring with a circle in it to avoid having to draw all the resonance structures. Aromatic rings are remarkably stable. Recall alkenes readily undergo addition reactions. For example, we can add a halogen like bromine across a double bond. Aromatic rings are stable enough that they do not undergo such reactions. If we expose benzene to bromine, no reaction takes place. Heat. Heats of hydrogenation can be used to quantify aromatic stability. Consider the heat of hydrogenation. If we have an alkene, it is 120 kilojoules per mole in terms of that heat. If we were to just about double it, we would have the information for a diene at -232, and if we were to triple it, we would expect it to be about 360, negative of course. However, from expected to actual, the difference is 152 kilojoules per mole, indicating to us that this ring is much more stable than predicted. MO theory can help us explain aromatic stability. The 6 atomic p orbitals of benzene overlap to make 6 MOs. The 6 MOs exist as bonding, 3 of them, and 3 as antibonding. In ground state, all 6 pi electrons go into the bonding MOs. The delocalization of the 6 pi electrons in the 3 bonding molecular orbitals accounts for the benzene stability. They are delocalized and all of the p orbitals overlap. 3. Criteria for aromaticity. Not all fully conjugated rings have aromatic stability. Some fully conjugated cyclic compounds react just like normal alkenes. Aromatic compounds must meet 2 criteria to be aromatic. 1. A fully conjugated ring with overlapping p orbitals, as we just saw earlier with MO theory. And 2. It must meet Huckel's rule. There must be an odd number of electron pairs, or 4n plus 2, total pi electrons, where n is equal to any whole number starting with 0. The conjugated compound below does not meet Huckel's rule and reacts just like an alkene. For example, this compound has 1, 2, 3, 4, or an even number of pair electrons that are p or pi electrons. So this compound, when exposed to bromine, will undergo addition. Huckel's rule. We can explain Huckel's rule using MO theory. Consider the MOs for cyclobutadiene, which has 4 pi electrons, or 2 sets, therefore it's an even number, and does not meet Huckel's rule. Because of this, it lacks a closed shell electron configuration and is unstable. Notice in its MO diagram, we have 2 electrons in the bonding MO, 2 unpaired electrons in the non-bonding MO. Because of that, it is anti-aromatic. A compound may be aromatic, anti-aromatic, or non-aromatic. Non-aromatic compounds do not have the instability of anti-aromatic. Let's go ahead and consider a compound, cyclooctatetraene, and the shape that it has. Cyclooctatetraene does not meet Huckel's rule. However, if the structure adopts a tub-shaped conformation, it can avoid being anti-aromatic. The conjugation does not extend then around the entire ring, it's broken. So the system is neither aromatic nor anti-aromatic. It is non-aromatic. Frost circles. Predicting the shapes and energies of MOs can be simplified by drawing frost circles to predict the relative MO energies. Follow the steps above to draw them. The first step is to draw a circle. The second step is to inscribe a polygon, making sure that one of the connecting points is at the bottom of the circle. The polygon that you make is the shape of your cyclic system. 3. Draw a horizontal line at each point of intersection. 1, 2, 3, 4, 5, 6, 7 with this example. Step 4. Draw a dotted horizontal line through the center of the circle, and then you can erase the circle and the polygon. Step 5. Identify all the bonding MOs below the line, non-bonding MOs on the line, and anti-bonding MOs that are above the line. Frost circles help explain the 4n+2 rule. Note that a number of bonding orbitals is always an odd number. Aromatic compounds will always have an odd number of electron pairs. Notice here we have from 4-membered rings all the way to 10-membered rings, and each time the bonding MOs is an odd number. For 4-member rings, it's 1, 5, 6, 7, 8-member rings, the number of bonding MOs is 3. For 9-member rings, it's 5, and for 10-member rings, it's also 5. Summary for aromaticity. Aromatic compounds fulfill 2 criteria. 1, a fully conjugated ring with overlapping p orbitals, and 2, meeting Huckel's rule, having an odd number of electron pairs, or 4n+2 total pi electrons, where n is a whole number starting with 0, 1, 2, 3, etc. Anti-aromatic compounds fulfill 2 criteria. 1, they will have a fully conjugated ring with overlapping p orbitals, but 2, instead of having an odd number, they will have an even number of electron pairs, or 4n total pi electrons, where again n is a whole number. When the compound fills criteria number 1, it is a non-aromatic compound. Annulenes. Annulenes are rings that are fully conjugated. Annulenes may be aromatic, anti-aromatic, or non-aromatic. In terms of the name, notice how the name is always annulene, and then we're being told the number of pi electrons, 6, 10, 14, in front of the name in brackets. Polycyclic compounds. Many polycyclic compounds are also aromatic, like naphthalene, anthracene, and phenethine. The stabilization energy that can be measured is done so by comparing the heats of hydrogenation. And notice below the table, stabilizing energy for a few polycyclic aromatic hydrocarbons is given. Ions, carb anions. Aromatic rings can contain negative charge or positive charge, either be carb anions or carbocations. Let's consider a 5-membered ring. 6 pi electrons must be present for it to be aromatic, since it has 3 bonding MOs. The way that this occurs, in order to achieve its aromaticity, it must then gain 2 pi electrons. The cyclopentadienyl anion has a lone pair delocalized over each of the 5 carbons. Note here all of the resonance structures, and therefore it is now an aromatic species as an anion. The acidity of the neutral compound, cyclopentadiene, is attributed to the aromatic stability of its conjugate base. Note here the hydrogen that is being extracted by the base is an sp3 hybridized carbon attachment. Normally for alkanes, we're talking about pKa really closer to 50. Notice here the pKa is about 16, making it a very acidic proton, resulting in a very stable anion. Ions, carbocations. Let's consider a 7-membered ring. It needs to have 6 pi electrons, one of the carbons itself must then have an empty p orbital in order for it to be aromatic. The compound needs to be cationic in that case. Notice here all the resonance structures that allow all the p orbitals to overlap, resulting in conjugation and Huckel's number of pi electrons. The troponium cation is an aromatic cation example. Aromatic heterocycles, heteroatoms, atoms that are not carbon or hydrogen, can also be part of an aromatic ring. Let's consider pyridine and pyrrole. If the heteroatom's lone pair is necessary for aromaticity, it will be included in the Huckel number of pi electrons. So let's consider our first example, pyridine. Because the benzene ring here with the N heteroatom already has the 6 pi electrons, it does not need that lone pair, and it should not be included. This lone pair of electrons will be in a perpendicular sp2 hybridized orbital away from the p orbital overlap. They are not included. But in pyrrole, that lone pair must be included in order to have the 6 pi electrons. So that lone pair is in p orbital, and the N is sp2 hybridized. Basicity. If the lone pair is necessary for aromaticity, then that lone pair will not be basic. Note, in the first example with pyridine, since that lone pair is not needed, it is going to be basic enough to extract H+. However, in pyrrole, the lone pair is needed, so it will result in a non-aromatic species, which is not as stable as keeping the aromaticity. The difference in electron density can also be observed by viewing the electrostatic potential maps. Notice in pyridine that lone pair is localized, in pyrrole it's delocalized, contributing to the aromaticity. 4. Benzylic reactions. A carbon that is directly attached to a benzene ring is called a benzylic position. Here are 2 examples of benzylic positions. Oxidation. Recall that aromatic rings and alkyl groups are not easily oxidized. If we have a benzene ring in the presence of a strong oxidizing agent, no reaction will occur. The same is true with something like an alkane that's acyclic. However, benzylic positions are oxidizable. Benzylic oxidation. Benzylic positions are readily oxidized by chromic acid. There's different ways to get to chromic acid. One method is to use sodium dichromate, sulfuric acid, and water as our oxidizing agents to get at the end a carboxylic acid. The benzylic position needs to have at least 1 proton attached to undergo oxidation. If the benzylic position does not have at least 1 proton, no reaction will take place. Permanganate can also be used as an oxidizing agent. Notice here potassium permanganate, water, and heat can have the same process take place on the benzylic carbon. Benzylic bromination and reactions. Benzylic positions are like allylic positions and readily undergo free radical bromination using MbS as a reagent and heat. Benzyl bromides are useful synthetic intermediates. Benzylic bromides readily undergo SN1 substitution. Unhindered benzylic bromides undergo SN2 substitution as well. Benzylic bromides are readily converted to the corresponding alkenes via E1 or E2 elimination reactions. Benzylic reactions flowchart. Make sure to know the flowchart. The benzylic position can undergo radical bromination. If it has at least 1 H, it can undergo oxidation. From this point, we can get to different types of derivatives or targets. Make sure to review Chapter 12, Reactions of Alcohols, and make sure to review reactions of alkenes if we end up with an elimination product. Reduction of benzene. Under Forcel conditions, benzene can be reduced to cyclohexane. Note the pressure, 100 atm, 150 degrees Celsius, the presence of a transition metal catalyst like nickel, and 3 equivalents of hydrogen gas will have this undergo reduction. However, alkenes can be selectively hydrogenated in the presence of a benzene ring. If we then do not have forceful conditions, an alkene can still undergo hydrogenation. Because the benzene ring is very stable, it will not be affected. Birch reduction. Benzene can be reduced via the Birch reduction. Here is benzene ring, and it can be reduced to a diene using sodium metal, methanol, and liquid ammonia. The mechanism is like dissolving metal reduction of an alkyne. The first step is the nucleophilic attack, and then proton transfer, followed by nucleophilic attack and proton transfer again. The Birch reaction continued. The major takeaway from this reaction is that it does not completely reduce the benzene ring. The product has sp3 hybridized carbons on opposite ends of the ring. If we do have groups attached to the benzene ring, for example, the presence of electron-donating alkyl side group, it will provide regional selectivity. An electron-donating group destabilizes the radical cation, and so reduction does not occur at the carbon possessing an electron-donating group. That means the product will result with the double bond still being present at a carbon that contains the R group, and then the sp3 carbons are on opposite sides of each other. The presence of an electron withdrawing group results in the opposite regional selectivity. For example, if we have this electron withdrawing group, notice that we have the reduction taking place at the carbon with that group attached to it. IR spectroscopy. Let's consider the characteristic signals in the IR spectra of aromatic compounds. Absorptions at 3000 to 3100 wave numbers is due to the CH stretching, and the C is sp2 hybridized or a ring C. Notice how we have them right here for a given aromatic compound. There will be combination bands and overtones. These are going to be weak signals at around 1700 and 2000 wave numbers. Between 1450 and 1650, we're going to see the stretching of the carbon-carbon bonds as well as ring vibrations. And then into the fingerprint region, we're going to see CH bending in the plane and out of plane as well. NMR. The integration and splitting of protons in the aromatic region of the 1H NMR is useful for rings with multiple substituents. Aromatic protons will be found downfield, but their multiplicity will give us information about their environment. In the carbon-13 NMR, carbon atoms of benzene typically appear approximately between 100 to 150 parts per million. The number of signals is helpful to determine the substitution pattern. In the proton NMR, we saw a couple of examples. In the carbon NMR, there are several more examples given here. Depending on the substituents, we might expect to see 2 signals, 3 signals, 4 signals, 6 signals. It just depends.